Okay, so let me talk about evolution of the calculus concept and idea, and I want to show you from my perspective what I mean by calculus. Okay, so let's start with this one. Okay, this one many years ago. I don't know, maybe 1,000 years ago. So this one here just over 300 years ago, fundamental calculus just so new. Oh, this thing here and this thing here about a few hundred years ago. Okay, but this one is like thousands of years ago. So now what mean by calculus from the very beginning? So you want to find the area of the circle, right? You don't know. So but you don't give up, right? You try to find the accurate as possible the area of circle. So in the past, people do like this. People construct the square. You know, that very easy using the compass. Okay, so then go like this. Go like this. So this one should be the square installed in the circle. Okay, installed in the circle. So now you know how to find it. You can using very basic construction, right? You do like in geometry. So maybe this one collapse, move back and forth doesn't matter. The concept there we assume this one is square. Okay. So if the radius, so this one has to be 45, right? The length is r. This one should be r root of 2. 45, 48, 90, and this is also r root of 2. So now they estimate by the area of a circle by the area of the square, and also they want to be more accurate. They do circumscribe square. This one inscribe, this one circumscribe. Circum mean you install the one is just outside of the circle. Okay, so now you add the area of this square. You add area outside square. One is overestimate, one underestimate. You divide by 2, and you have the area of the circle. Okay, the small square is r root of 2 square. You add to the big square. This one has to be 2r, right? Because radius equal r, the diameter equal 2r. So plus 2r square. You add the big with the small, and you divide by 2 to estimate the area of the circle. So you have 2r square plus 4r square divided by 2 give you 3r square. Remember, the area of circle is pi r square, right? This one super close in terms of 1,000 years in the past. This one very accurate because it's not so simple. You see how people fight very easily, right? They almost like very accurate, you know. So now the idea keep evolving. So people agree that if you do more, you do a hexagon, for example, or H side. So if you do the H side, you know, like this, so you see that the arrow making a lot smaller, right? And you go like this, and go like this, and you increase the accuracy a whole lot if you divide by H side. Okay, this one you call the octagon. So you see this one shrink into very small instead of very big, right? And people agree that if you divide many, so we don't need to do outside, inside enough to very accurate. Okay, divide by, how about if you divide by 16? So what happened? You're going to have the 16 gone, become like this. So the error getting very small now. 16, you have divided by 16, 16 isosceles triangle. Okay, so like this. So now the error shrink into very little here. For example, you divide by 16 of them, right? So the error become shrinking. How about you divide by 32, 64, and so on and so forth? And people trying to do to estimate as possible. Okay. Okay. Last time we did, you divide by 6, and the number here become 3.06 or something. So improve, right? If you keep dividing and you don't keep going to the pi, going to astronaut. So how to do this? In a few years ago, we have some method of Riemann sum. We will function, but this one go before the Riemann sum. When we discover the limit, we can find it by making n go to infinity. So how it works? So let's go back to the original circle here. Okay, I go back to the circle here. So now, after people do like divide by so many of them, and people calculate by hand, people don't want to do it anymore. So people want to find exact value. So after discovery of the limit, proper limit, and what people do, take a look at this. Okay, so now the argument here is if I divide by n triangle, for example, I have the center here. I make it big because actually the triangle very small, but I make it big for you to see the procedure how to find it. So I divide by n triangle. Okay, isosceles triangle, n of them. So the radius equal r. Okay, so therefore if I divide by n, therefore the angle here have to be 2 pi over n, right? The total 2 pi divided 2 pi over n. So now I try to cut by half. So I cut this one by half here. Okay, so now the angle here, half of that had to be pi over n. So now I try to write equation of the area, this one in terms of n and r. So now remember the angle here, and this one r here, and this one has to be r over 2, right? So but this one had to be r psi of pi over n, because psi of pi over n equal, this one right angle, psi of pi over n equal opposite over r, therefore the opposite equal r psi pi over n. The same thing here, the height of the rectangle of the triangle here equal r cosine pi over n. Okay, because cosine pi over n equal adjacent over hypotenuse, right? Therefore, this one equal r cosine over n. So the area of big triangle equal half of the very width of this times the height. So the area of triangle equal r, this one times this one, you get r squared sine of pi over n cosine pi over n. So that is one single triangle. Then we have n triangle. N can be any, like if n equal 4, you put 4 here, 4 here, 4 here, you will have, that's what I did last time, okay, if n equal 4. If n equal 6, you put 6 here, 6 here, 6 here, for example, and you estimate the area of the circle, okay. If n equal 6, what happens? You put 6 here, r square here, sine of pi over 6 equal 1/2, and cosine pi over 6 equal root of 3 over 2, right? So it turned out to be 6 over 4 is 3 over 2 root of 3 r squared. This one likely very close to pi. How about if n go to infinity? So if n goes to infinity, everything here come out to be pi for sure. Okay, well, let's see if we're able to do that. So now here I take the limit and go to infinity to see what do I have. Okay, so okay, now let's see. So we apply a limit, we apply this limit sine of theta over theta. When theta goes to 0, everybody already master this one equal 1. Or limit sine of 1 over x over 1 over x going to infinity also equal 1, because when x goes to infinity, this one turn out to be 0. Okay, the other way to say. Okay, so now I try to get this one. So if I put n going to infinity, this one become 1, right? Because n go to infinity, cosine of 0 equal 1, right? But we don't know about this. Sine of 0, these are not sine of 0, you cannot put, okay, so we don't know about this. So what we know is you have to do, you divide by pi over n to match with this one, okay, match with one. At the same time, when you move to in the bottom pi of n, you have to multiply by top, the same thing, right? Okay, then you take a limit, okay. So limit n go to infinity, so this n here, you cancel that n here, Okay, so this one turned out to be 1. You have r squared right here, and this one also equal 1 because cosine 0 equal 1, and you have pi. So this one here is, let me introduce the Riemann sum, or from the concept Riemann sum, early Riemann sum. Then after that, we will limit Riemann sum to turn this concept into the perfect exact value of the integral. Okay, then I introduce the definition, what I mean by that, and finally we reach a fundamental theorem, calculate part 2. I skip part 1 because this connect all of the material connect together. So part 1 I talk about different time, okay, different video. So Riemann sum, let's say this is a function f and positive, okay. It can be negative, but I make it simple because I want to introduce you the concept, the general concept only. We don't want to go to detail at this moment. So how to find the area of this? So the same with the problem with the circle, Riemann start to divide this by n, a rectangle, right? So you can use the right hand, then he called this one a here, from the point a here equals h sub naught, h sub 1, and you divide by n of them, h sub 2, and so on. Dot, somewhere here is h sub I. Okay, you have many of them. Okay, many of them. So, and continue to get the next one. For example, h sub I plus 1, and so on. This one h sub n. Okay, so now here is a Riemann sum. Let's do the right hand, easier to explain. Okay, this one right hand. If you don't like the right hand, we can do left hand. We start from h sub naught here. So you find the area of this one, at area of this one. In this case here, the right hand overestimate and the left hand underestimate. Okay, so let's do the left hand, the right hand first. So now the area number 1, add with area number 2, add, and you estimate the area under the curve f of x from A to B, right? So then the first one is f of h sub 1 times delta h, the length times the width here, we call delta h here, delta h. The second one, f of h2 times delta h plus f of h3 times delta h plus dot plus f of hi times delta h plus dot f of hn times delta h. In this case, n could be from A to B. Okay, so now we didn't represent the Riemann sum. Each of them is the length times the width, the length times the width, the length times the width. Okay, so if you factor delta h out, and you're going to have f h1 plus f of h2 plus f of h3 dot plus f of hi dot plus f of hn, the whole thing here times delta h. So that is the Riemann sum. So now people develop the notation for Riemann sum, right? Remember the notation, it become here f of hi delta hi from 1 to n. So this one we call the Riemann sum. I equal 1, you put 1 right here, you have that one, f of 1. So delta h there, I equal 2, you put h2 right there, but this one means you sum up them together. Okay, you not list them. Okay, if we do like this, f of hi delta h, then you have I from 1 to n. Then this one means you have the sequence, you have this comma, okay, this one you add up all together. So this one we call the Riemann sum. Okay, where the graph going down to negative, that's the same thing. Okay, but I want to do positive to make it more simple. Okay, so now what the limit of Riemann sum? So the concept here the same. We estimate the circle area of the circle, right? If you divide more, the area here is shrinking into less, right? For example, if I divide this one, look, I divide by 20. If you divide by 40, so each of the area here shrink in half. You do like this, so you go like this, and you go like this. So this one disappear. So the error become much smaller if you divide double it and you double again, and it shrink into this one. The error here shrink to 0. So we call the method of exhaustion. Okay. So by take a limit and go to infinity. So I want to do it in red here. Limit and go to infinity. So now when you n go to infinity, this one here shrinking to 0. So we call method of exhaustion. You exhaust the error into 0. So this one here is make the limit is a 2 of congruous. It says it's not congruous. Who say limit congruous? I disagree. The limit is a tool to carry the concept into the perfection. So after you do the limit like I did before, right, the circle become, the arrow circle become perfect. Now I repeat again. So the concept of Riemann sum is u divided by n, okay, rectangle, and you add all the area of rectangle together like this, the width times the line, the width times line. So many of them to estimate the area under the curve. So now the concept is if you divide by more rectangle, that means n increasing. So this area here becomes smaller and smaller. So we call the method of exhaustion. So then finally you able to find the limit. You have the skills, you have the technique, you have the skill how to take a limit. The concept then carry this estimation become the perfect. Okay, if you're able to do that, so you're going to have the perfect. So the method of exhaustion is to exhaust all of the error into 0. So now you have the perfect area. Okay. Now this one here, okay, this one here they give a definition because that's too cumbersome, right? Too confused, too big, right? So they make it like from here, from A to B, f of h dh. Okay, so this one here is just a definition of that. This one nothing else. This one here just they make it more simple. They use different notation. This one delta h here to me is the fixed number because the n here is fixed. Okay, n. This one here delta h. I'm not talking about limit yet. So the Riemann sum, the piece here Riemann sum. Sum. So delta h Riemann sum divided by n. N can be a zillion, but this one still the fixed one, not moving. But when you take a limit, this one shrinking to 0, it will keep shrinking. Therefore, they have to change the notation to make sure this one different ID from that one. This one fixed one, this one fixed one, this one not fixed one, keep going to 0. Okay, because when n go to infinity, the same meaning with dx is 0. So now f of x is you don't need I anymore because there's too many n, right? So you divide by too many of them. So you don't need to location anything. So just f of x the line from any x over there. So this one is the definition of the limit of the Riemann sum. Okay, the definition is this. Okay, so this means this. So people guess this one like a s, right? Sum, right? And this one clearly in Greek, this one the sum, the word of the sum, and this one also the sum. But this one kind of keep. This one is the whole thing, but this one not equal to that one. Okay. Okay. So now finally, from here to here. So what happened in the history? Newton discovered this without doing any of this. So we work so hard to find the area using this method, right? You try to manipulate to find the area of the limit, right? But now Newton say you don't need to do all this thing. All you need to do is you take antiderivative of this. So now notation is f of x is the antiderivative. This if f prime of x equal f of x. So this one antiderivative this one, you're able to do that, and you evaluate from A to B. Okay, which means f of b minus f of a. So you need to know antiderivative of b, you subtract antiderivative of a, you have this one without anything in between, you don't care. That is wonderful. So these are most important discover internal application. Okay, so these are powerful application. So from them, after Newton, you can apply this to do a lot of problems in physics, a lot of problems in any area, different area, include navigation, include, you know, everything. Spaceship, whatever, you use this one. Okay, that was a breakthrough for the mathematics. Now, I try to show you again. Now, we apply the fundamental calculus to find the area of the circle. Remember, we did that with a limit, right? With a Riemann sum, everything like that, right? So, now I try to write equation for this one, a function. So, I have y square equal r square minus h square. So, y equal, take a root both sides, root of r square minus h square. Okay, plus and minus. Now, let's say plus the upper half of the circle and minus the lower half. So if I take care of lower half, we cannot have the we cannot have the function. So therefore, I find only the half of the circle and multiply by 2. Okay. Okay. So now fundamental calculus. If you find the area from negative r to r here, right? All you need to do is write the function here, root of r square minus h square dx, right? You aggregate from a to b, okay, which is from minus r to r. Okay, this one here is represented by the area of the circle, and you multiply by 2. So in the future, you can find this one using a trick substitution. Okay. So, but at this moment you don't know yet, so I temporarily stop from here, and when you go to chapter 7, you will discover that one, okay? So, fundamental calculus, you just try to enter the tip of that, aggregate from r to minus r, and you go to find